Hello, so we can transfer loads from motion. The motion environment is found in the tools menu. So let me IPA inside a subassembly. As you can see, it's a motor driving some gears and a blade, a saw blade up and down through a mechanism. We can position the mechanism in the worst case scenario on the left side here. Maybe from that angle it would be easier to position. We notice that we have some constraints already positioned on some of the parts that are being studied in the simulation with the simulation tool. So some constraints, some fixed constraint and sliding along surface constraints have been placed, and connectors between the two parts that are being analyzed. The ones we saw when we initially entered the subassembly, except the vertical part. So if you go to the tools motion environment, you can simulate the mechanism with kinematics. If you upgrade Simply Motion to Motion, you can actually get graphs and add loads and also create contacts and couplers. So that's what we've set up here. We can run the study and we can see that the mechanism can be simulated. During the calculation, the load on the blade, which is 100 pounds as the blade is coming back up when it's cutting, and 15 when it's piercing through the wood, is going to be applied through the mechanism. And we see that the static study that we've done in FEA has been detected. So we will be able to transfer load that way. So here, if we move through the replay of the animation, we can see the system. We can see the velocity increasing when the blade is coming down at the top here. And we can see that the load is only 15 pounds when it's going down. When it's going back up, though, the velocity is inverted because the movement is up, and we have 100 pounds applied on the blade. So this results into some loads on the cam bearing, let's say in particular. That's where we're interested. So I'm going to add some loads on that part. If we close motion and we look at the static study done with the simulation module, we see that loads have been added to our study 1. Some of the loads apply to let's switch configuration so we can see only some of the parts. Maybe also hide this part here. So we had those constraints already, the fixed, the slide along face, and also the connectors between the two parts here. But the loads have been added. So some of the loads are actually not really that important for me. The gravity is negligible in that case, and the loads that are applied to the inside of the cam bearing, the inside cylinder of the cam bearing, is not necessary because the connector is going to transfer some loads through the cam bearing to the pin, which is held. So those inside forces are not actually relevant. So the torque can be maybe colored a different color, maybe orange, just so we can see 17 here, and the load that goes straight down here is 99 pounds. So we see that the load, the initial 100 pound on the blade, got transferred to the cam bearing in a more refined way through the mechanism. So this can result into a new study where we can detect the stress on the part and also look at the safety factor of our assembly. So just to remind you that simulation uses FEMAP for meshing and NX Nastran for solving. We do everything in the solid edge interface though, so it's possible to look at results directly in our interface here. For example, the safety factor. and maybe we can put a scale. The scale start at 2.6, the minimum safety factor, and the maximum safety factor could be, let's say, 8. So we see that we're in a pretty good scenario for that part, those two parts here, because everything is above 2.5, even the worst region here.